Hello everyone! Today, we will be studying Section 4.4, Operational Principles of Digital Currencies from the course Development of Digital Currencies. A central bank digital currency, CBDC, is much more than a simple electronic ledger. It is supported by a carefully engineered operational system. In today's lesson, we will explore how CBDC is issued, circulated, and secured, revealing the fundamental logic that underpins the digital financial era. The session will examine CBDC across four core dimensions: system architecture, representation of value, key technologies, and underlying design principles. By the end of this session, you will be able to 1. Understand the two-tier operational framework, connecting the central bank and the commercial banks. 2. Differentiate between account-based and token-based CBDC models. 3. Appreciate the protective role of key technologies within the system and understand the principles guiding CBDC design. Everyone, why is the central bank commercial bank two-tier system considered the core architecture of digital currency? Let's start by considering a top-level design question. Who should distribute a CBDC directly to the public? Should the central bank issue it directly, requiring every individual to open an account with the central bank? Or should we leverage the existing commercial banking system? The prevailing choice globally is the latter, the two-tier operational framework between the central bank and commercial banks. Why is this model preferred? Let's examine the roles of each tier. 1. Central bank tier, the issuance hub and the ledger manager. 1. Core functions, currency issuance. The central bank is the sole creator of CBDC. Digital currency is generated within its core system, essentially representing the central bank's digital liabilities. Ledger maintenance. The central bank maintains the authoritative ledger, recording the total CBDC supply and its allocation among commercial banks. Rule setting establishes issuance rules, technical standards, and compliance requirements. 2. Key roles: ensure monetary sovereignty, control financial risks, and maintain the authoritative finality of the system's settlement. 2. Commercial bank tier, distribution hub, and user service provider. 1. Core functions: exchange and distribution. Commercial banks convert CBDC balances on a one-to-one basis, using their reserves held at the central bank, and provide exchange services to the public and businesses. Wallet operations: open and manage digital wallets for users, conducting customer identity verification, transaction processing, handle user-to-user transfers, and implement transaction monitoring. 2. Core value: leveraging the existing banking infrastructure, commercial banks can reach a vast user base, provide convenient payment experiences, relieve operational pressure on the central bank, and contribute to financial stability. Thus, the core logic of the two-tier architecture is: the central bank manages the macro level, issuance and regulatory framework, while commercial banks handle the micro level, circulation, and user services. Each tier performs its own role, creating complementary advantages. So, the CBDC distributed to us by commercial banks, what form does it actually take? This brings us to our second dimension, the representation of value. 1. Account-based CBDC, identity-linked balance records. 1. Operational essence: Users hold verified digital accounts. At the central bank or commercial banks, the CBDC in your account is essentially a string of balanced numbers. The core of any transaction is verifying the payer's identity and adjusting balances across the relevant accounts. 2. Characteristics. Advantages. Easily integrates with existing regulatory frameworks and facilitates targeted monetary policy implementation. Challenges. Relies on a centralized identity system, raising privacy concerns, and the system's centralized nature demands very high stability. 2. Token-based CBDC, cryptography-based units of value. 1. Operational essence. CBDC exists as encrypted digital tokens, each representing a specific value. For example, 1 yuan. Owning a token is equivalent to holding that unit of value. How do you prove ownership? Through your private key, much like holding the key to a personal safe. 2. Characteristics. Advantages. Offers enhanced privacy at the transaction level, especially for small value transactions, and supports the potential for peer-to-peer payments. Challenges. Balancing privacy and the regulatory oversight requires additional design considerations. For example, a controllable anonymity model. And users must safely manage their private keys. Regardless of the model, secure and efficient operation relies on robust technological support. Next, let's explore the core technologies that underpin CBDCs. A CBDC is a complex system that requires the coordination of multiple technologies. We can summarize its technological foundation into 3 key pillars. 1. Distributed ledger technology. DLT, selective application. Its role is to provide participating institutions, central banks, commercial banks, etc., with a shared, synchronized, and tamper-resistant platform for transaction records. Applications include 1. Wholesale domain. Optimizes large-value interbank payment settlements, for example, cross-border project mBridge, improving efficiency and reducing risk. 2. Retail domain. Applied more cautiously with emphasis on central bank control, performance, and privacy protection. Advantages and considerations. Enhances transparency and tamper resistance. Facilitates multi-party collaboration but must address challenges related to performance, privacy, and energy consumption. 2. Cryptography, the security backbone. Core applications. 1. Digital signatures. Ensure transaction authenticity, integrity, and non-repudiation, especially critical for token-based CBDCs. 2. Data encryption. Safeguards the confidentiality of transaction data and user privacy. 3. Secure communication. Guarantees the security of data transmission channels. 4. Token security. Prevents counterfeiting and double spending attacks. 3. Smart contracts, the programmable engine. Smart contracts are self-executing programs that trigger automatically when predefined conditions are met. Typical applications. 1. Conditional activation. For instance, automatically invalidating expired consumer vouchers. 2. Restricted fund usage. Directing payments to specific purposes, such as earmarked loan disbursements. 3. Complex transaction execution. For example, implementing delivery versus payment (DP) in securities trading. 4. Regulatory support. Automatically reporting, large value transactions to authorities. Benefits and risks. Smart contracts can greatly enhance operational efficiency and reduce human error, but since code effectively serves as law, it is crucial to ensure the security of the code and its compliance with legal standards. All these technologies converge to support the core design principles of CBDCs. Next, what are these guiding principles? Let's continue our exploration. 1. Privacy, protection, and controllable anonymity. Implementation approaches. 1. Token-based foundation with tiered wallets. Small value transactions, basic wallet, focus on validating tokens and signatures, while minimizing identity linkage. Large value transactions, advanced wallet, enforce strict real name verification with full traceability. 2. Data isolation. Transaction data and identity information can be managed by different institutions, central banks, commercial banks, reducing centralization risks. Legally traceable under legal authorization. Technical mechanisms enable the tracking of illicit transactions. 2. System resilience and security. Safeguards. 1. Redundant architecture. Critical systems are deployed across multiple nodes and locations to prevent single points of failure. 2. High-level protection employs state-of-the-art encryption standards and cybersecurity protocols for continuous defense against attacks. 3. Business continuity. Comprehensive contingency plans ensure basic payment functions remain operational under extreme conditions. For example, dual offline payments. 4. Physical security protects data centers and hardware infrastructure. 3. Interoperability, the key to an integrated ecosystem. Requirements. 1. Integration with legacy systems. Enable seamless exchange and coordination between CBDCs and bank cards. Third-party payment platforms. For example, Alipay, WeChat Pay. 2. Cross-border connectivity. Promote harmonized technical standards and regulatory frameworks. For example, mBridge project to achieve efficient settlement and exchange across different national CBDCs. 3. Broad merchant acceptance. Ensure users can conveniently use CBDC wallets across diverse consumption scenarios. Everyone, the operational mechanisms of central bank digital currencies, CBDCs, vividly reflect a nation's comprehensive considerations. In the digital economy era, covering monetary sovereignty, financial stability, technological innovation, and public welfare, CBDCs are more than a payment revolution. They represent a critical infrastructure for the future digital economy. To understand them is to gain a key perspective on the evolution of future financial landscapes. It is hoped that today's lesson helps you build a deep and structured understanding of CBDC systems. See you for the next lesson.